Okay, time to get going. I hope you all had good breaks. I saw different things like, Caitlin went to Florida and Jerry went to California and Sandy got engaged. And hope everybody had a good time. And congratulations, Sandy, because that's far more important than any physics class. It's a life. Yeah, it's a full life decision. You can't fail at that one. No implication there. Simply, it's not. Man, that did not come out right. Getting an A, B, C, D, F in physics is not a life-defining moment. But getting engaged is what I meant to say. And you go, that came out horribly. But while I'm uncomfortable, I have the test graded. They'll be probably record this afternoon. I have meetings from 12:30 until 4, I think, today. So I won't be in my office hours, but I'll try to get them posted after that. The test scores, there were some really good scores, like, a handful that were 95 or so. But there were also some really bad scores. And, if you scored less than 50%, it would really be wise to come talk to me. We can try to figure out, okay, so what's not working out? How can we achieve success? Because I am sure for every teacher, the goal is for everybody to get A's. And, when people are getting low grades, that's disturbing. And I want to help the students try to make sure that success is achieved. So if you have a low score, please come talk to me so we can try to work things so that you'll understand better. That said, let's move on with optics. So we ended last class period talking about how lenses and mirrors work, and we had simple things like for a mirror, the focal length of a mirror is equal to 1/2 of the radius of curvature of a mirror. Right, that's the last slide that I had for our lecture on Friday before break. And for a lens, we didn't actually show the lens maker's equation. I believe it's like this. Like I said, we didn't show it. I didn't look it up beforehand. But the focal length of a lens has to do with the index refraction of the material the lens is made out of and the radius of each of the two surfaces. So you can get the same focal length with lots of different combinations of the radius on the first surface and the radius on the second surface. And I did mention that the different shapes of the lenses are because if you have something that's far away, you would want to have a curved surface on the side close to it and a flat surface on the side away. You're trying to achieve getting half of the change of direction, half the refraction on each surface. Now with those, we had the simple geometric relationships that we could always use. And that gave us 1 over focal length is 1 over distance image plus 1 over distance object. And I showed you that there are different symbols that can be used. Sometimes they'll use like S and P, or like P and P prime. There are different symbols that are used by different people in different books. So you have to just kind of pay attention when you look through sources to what symbol they're using for object distance and image distance. And we had our sign conventions that if an object, okay, I probably didn't cover this as full. Oh man, I need to take that back. They need to use that at the high school. If an object is on the side light is coming from, then it's a positive object distance. If it's a real object, that is, if it's something like a candle or a pencil or a person, it's always going to be a positive object distance. The image, if the image is on the side that the light goes to, then it's a positive image distance. So for a mirror, since a mirror reflects the light, it's a positive image distance if it's on the same side as the object. But for a lens, since the light goes through, it's a positive object distance if it's on the opposite side from the object. And then finally we had magnification, which was defined as height of the image over height of the object, and turned out was mathematically equal to minus the distance image over distance object. And you remember Megan and me carrying these mirrors up to Megan and her describing what it looks like as she got closer. And you saw that it was forming an inverted image. If it's inverted, what is it always going to be? Real. Now, I have to give you one caveat. If it's a single lens or a single mirror, if it's inverted, it's always going to be real. If you have two things, two lenses or mirrors, it could go either way. But for single inverted, it's always real. If it's upright, then it's going to be virtual. Virtual means the light rays don't really meet where our brain thinks they met. Real means they really met there. You can put a piece of paper there and you'll see it on the paper because the light rays are really there. So that's a quick review of what we've done. Now we're going to look at our first optical instrument, the one that I believe God created in us. Now, just because I know not everybody here is creationist, probably not everyone here is even a Christian, and that's perfectly fine. But one of the things that helps me have less confidence in the evolutionary ideas and more confidence in the creation is looking at the human eye, or the eye, mammalian eye, I should say more accurately. The mammalian eye appears in virtually every million species that diverged at the Cambrian explosion. Cambrian explosion, 542 million years ago or something like that? The time when you went from trilobites to having a wide range of different types of species. And you have very similar structures in the mammalian eyes for everything that came from that. I say mammalian eye, there's other eyes that also have the similarities. And by evolutionary theory, that means that you already had this very complex thing that is shared by all these species that diverge there, developed at the time of the Cambrian explosion. If you're going to follow an evolutionary idea, the theory is that things should have been simpler back then and become more complex. And so we should have a lot more variation in our eyes, unless this is the only way that works, or we were created. Okay, so that's not physics, but just throwing a little bit in there. I want to make sure that, my class, you can't separate it from religion. I still burn because about 20 years ago, one of our Seventh-day Adventist institutions actually won a lawsuit that they were not pervasively sectarian, meaning that your classes, like your science classes, had no religion whatsoever in them. Okay, so I try to make sure I have it from time to time. Let's talk about the eye. The eye is, well, we see a lot of parts here in this picture. Clearly, I'm not a biologist. I'm not into anatomy all that much. But the first thing we have, I had two students who, they were in class together, and their parents were both ophthalmologists. And I said, the first thing is the cornea. And they're all, no. You have the sclera first. And I said, well, the cornea does all of the focusing. No. The sclera does, because it hits there, and that's where you have a refraction occurring. Okay, so just to be really clear, almost all the focusing in the eyeball is done at the front surface of the eyeball, which is shaped by the cornea, but has a thin layer of membrane that I believe is called sclera that is going over it. And so that's your primary focusing element. So if your cornea gets misshapen, like my grandfather took a hockey puck to his eye, that damages your vision because that takes away your ability to focus right. So light comes in and gets focused by that first surface. So from now on, I'm just going to say by the cornea. I'm going to say the cornea is the first lens, the important lens that does almost all the focusing in the eyeball. After it goes through the cornea, you have a layer of fluid. That layer of fluid we call aqueous fluid or aqueous humor, and it's essentially like water. It has essentially the same index refraction as water. And then we hit the iris. The iris is a membrane that can expand or contract over the next piece, which is the lens. So the iris expands or contracts. The purpose of this is to control how much light gets into the eyeball. because you have a sensitive light detector back there. If you put in too much light, it loses sensitivity. If you put in too little light, it doesn't have sensitivity. So the iris is controlling that amount of light. So our brain ties into how much light is received to the back and uses that to control the iris. So how many people in here have at least taken an EMT class? Only Brandy? Okay, it's you and me. So you have somebody who has been in an automobile accident. And in your trauma protocols, one of the things you do is you take the light and you shine it in their pupil and then you turn it away, right? Why?
Make sure that their will dilate so that they're still getting like nerve sensation to the eye.
Yeah. It tells you a lot about the brain's working, because in the normal situation, you put in that bright light and the pupil very quickly closes up. And then you put it in dark and it opens to try to keep the amount of light constant. So, normal and responsive is the term you want when you're doing that test. But sometimes the pupil is blown. The pupil, by the way, is the hole in the iris. What does it mean if the pupil is blown?
Probably bleeding in the brain, probably pressure on the back of the eye.
Okay? Blown, the pupil is wide open. Because like when I was taking EMT class, they're saying the pupil is blown. I'm thinking like, so, something's come through it. No, it's as open as it'll get. And if it's not responsive to light, that's a bad thing. And then you have, other things. It can be constricted. It can be doing random things. If people are on drugs, they do random things. Like they go, because the brain isn't working right. Another thing that you do is check if their eyes can follow your finger. And if a person's brain is working right, it'll just track automatically, right? But if it's not working right, you know how they say drunk drivers lose their motor control? They lose that as well. They'll do things like your eyes work like blinkers. They'll go trying to follow instead of being smooth. So the eyes tell you a lot about the brain's function. So we have the iris. It opens and closes to just the amount of light. That iris is what gives us our eye colors. It's just pigmentation giving it color. Then we have the lens. And naively, you would always think, well, the lens must be the important lens in the eyeball. It's the secondary lens that gives us what we call accommodation. It allows us to change the focus so we can focus on things that are near or things that are far. So that's the point of the second lens. Now, this is one of those amazing things. See, this says ciliary fibers. You have those ciliary fibers are attached to muscles, and it's kind of the reverse of a sphincter. Instead of squeezing down, it pulls out, and at least I think that's how it works. I'm not, like I said, not a biologist, but you actually deform that lens with those ciliary fibers. So it changes the shape of the lens. If it's more curvature, then it's going to have a shorter focal length and thus be a stronger lens. Now, the index refraction, I said that the aqueous humor has an index refraction that's essentially the same as water. The aqueous humor has, and I'm just going to put H for humor, 1.334. The lens is somewhere around 1.4. So the index refraction is not very big between the lens and the aqueous humor. Right? If you go from the air to the cornea, it's a difference of 1 to 1.33. You go from the humor to the lens, it's like 1.334 to 1.4-ish. That's a small difference. What does that tell you about the refraction? It's going to have little, not much, refraction because it's not much difference in speed. Remember, please, no food or water at the tables because now they're using nasty chemicals at the tables. So we go through the lens. The next thing is the vitreous humor. Basically the same thing as the aqueous humor, like water. Goes through there and comes to a focus back here on the retina. Now, the retina has pieces like the fovea, the place where you have the most sensitive material. But the retina detects the light, sends it down the nerves to the brain that makes our picture. So that's how the eyeball works. it's not super hard to understand, but it's reasonably complex. And as you study it more carefully, you find that it's more and more complex. So we're not going to get into all the complexities, but that's the way the eye is. This thing here, where the optic nerve attaches, we're blind there. So we have a blind spot, a place where the retina can't detect. And you can do little tests to find where the blind spot is just by seeing where you suddenly can't see something. You don't realize it's there because your brain is pretty amazing and just fills in details. So, how's an image formed? We have something that's far away, like a tree in this picture. We have that light from a large distance away, and then light rays. Notice we have light from the top of the tree going in rays 1 and 2. Rays 1 and 2 are going like this, and rays 1 and 2 meet there. Where rays 1 and 2 meet is where we're going to have the real image from our object. Now notice that tree. The tree is inverted because it's a real image. I'm going to go up and down with this today. Which is probably not the most efficient. Here I have my eye model. For lab, tomorrow we're going to be dealing with the eye. So here's the eye model. Ideally, if I have parallel rays, I'm looking at something very far away, my eye should make it so the light focuses on the retina. So if I put something in here, there it's focused on the retina. See all the rays coming together there? And I would have a clear image. That's the way the eyeball is supposed to work. Now, to avoid going back and forth, I'm going to go straight to some vision problems. Here I put a different lens. If your cornea is the wrong shape, you can have a problem. In this case, is the cornea too curved or not curved enough? Too curved. There's a second way of thinking about this, of describing it, and that is to say that the eyeball is too long. It's a geometry problem. The shape is wrong no matter how you cut it, but you can either say the eyeball is too long or the cornea is too curved. So in the good old days, the days when I was born, what you did if this happened is you got glasses. And what do you want those glasses to do for you? You want them to diverge the light a little bit. So I have up here two corrective lenses. Should I choose the converging or the diverging? Diverging. So I put the diverging here. And now you see that, it's coming to a focus in the back of the eye again. I now have a corrective lens that's fixed this problem. So that's why we can fix this problem. The problem of too curved is called myopia or nearsightedness. Now, just to make sure you can see what's happening here, I'm going to move this lens out. So you can see what's happening to the light after it goes through this lens, but also know what happens to the focal point if I move the lens out. So you can see it diverge. But when I moved it out, what happened to the point where it came to a focus? It moved in a little bit. So the positioning of this matters. So if you take your eyeglasses and you hold your eyeglasses like out here in front of your face, they're not going to work for you as well as if they're in the proper location. So the prescription for your eyeglasses is based on the eyeglasses being a certain distance in front of your eyeball. For our homework problems, unless it says otherwise, assume that distance is 2 centimeters. That the lenses are 2 centimeters in front of the eyeball. If it says another number, of course, use that. So this was myopic vision having too curved of a cornea. We can also have hyperopic. It's coming to focus way out here. So hyperopic, the problem, if you're going to talk about the length of the eyeball, what would the length of the eyeball problem be for hyperopic? Okay, the eyeball is too short. Or if you're going to talk about it as a lens problem, what's the lens problem? It's too flat, not curved enough. So we need to now make the light converge more. So I'll put a converging lens in front. And voila, it's in focus again. So that's how we do the corrections for eyeglasses when we have vision problems. We put a lens there that will, excellent, I missed the button. Probably missed that one. Nope, didn't miss that one. We put a lens there that will correct the problem. Now, I'm going through slides that are going to show us prettier pictures instead of my little demonstration with optics of these things. So, well, this is just showing an image formed. Accommodation is what we call it when you adjust your focus so you can see something closer. What does the accommodation? What's doing the adjusting? It's the lens, sometimes called the crystalline lens. So if you look at the shape of the lens here, and my hand-eye coordination is such that I can almost do this. The shape is quite different. Your muscles deformed that crystalline lens to make it accommodate, adjust the focus. So here's the two different ways of talking about problems. So the top part, myopia. Common name for myopia, nearsighted. So if somebody says, he's so myopic, what they mean is he can only see the problems of today and can't see how it's going to affect things in the future. You know, doesn't have any vision about the future. It's just everything's for right now. If you're myopic, or myopic, some people say, you can see fine close to your face, but you get farther away and you can't. So with this nearsighted or myopic vision, we talk about the far point. The far point is the farthest point that you can focus. Ideally, your far point, how far should you be able to focus? Ideally, how far should you be able to see clearly? Infinitely far away. So the ideal far point is infinitely far away. But in reality, it's not. So, Jared, help me out. Oh, wait, no, don't help me out. You're not wearing glasses. Gila, you're wearing glasses. Take them off. And now hold this with the center side so that it's right next to your eyeball, obviously not touching your eye. And then just take your finger and move it out and tell us what the closest is where your finger is in focus and then the farthest before it goes out of focus. So what she's going to measure is her near point and her far point. Okay, 9 centimeters for the nearest. Excellent. Okay, so we have the nearest point that she can focus on and the farthest point she can focus on. Now, when she puts those glasses on, her far point, the farthest point she can focus on, the screen should be clear, right? If the screen's clear, you know what? As far as you can tell, infinity's clear as well. Right? The far point, if your far point's more than a meter, you don't need corrective lenses. Right? It's only if it's closer than you need them. So that's how I can, with confidence, know that she's going to be able to find it here within arm's length. Okay, near point is 9 centimeters. What we can consider ideal is near point is 25 centimeters and far point is equal to infinity. Now you say, wait, so what you're saying is Gila's near point is better than ideal. Wouldn't that seem to make sense? She can focus on things closer than the ideal eyeball. But the downside is she can't see far things very well at all. She can only see out to, 32 centimeters. So what we do is we do a correction for this, and we're going to correct the far point to ideal. So now with Gila, she has which type of vision? Is it myopia or Hyperopia. How did I know that before we started? You're right. Myopia. There have been worse things. How I knew was just playing the odds. The odds are there's no one in here who is hyperopic. Everyone is myopic. Myopia is very common. Hyperopia is fairly uncommon. So I was just playing the odds there and assuming that she was myopic. So with myopia, you're correcting the far point to ideal. So what we do, and so I'm going to draw a figure. Here's my eyeball. This is how physicists draw eyeballs. We're very consistent on this. And I have an object at the ideal far point. Now, this would be normal. Object is infinitely far away, and I want to make an image. But I can't focus on that image in the eyeball. So I'm going to put a lens in front of the eyeball that's going to make an image. So now I have to correct this back to the way I started. That's going to make an image on the same side as the object. If the image is on the same side as the object, is that going to be virtual or a real image? Virtual. Is it going to be upright or inverted? Upright. Okay, so I'm going to make a virtual upright image that is at her actual far point. So I'm going to have an image here, and the distance image will be at her actual far point. Now I have to do a few more things to make sure we've got things right. The far point is measured from the eyeball. The distance image is measured from the lens. So if I've run out of space. My distance object is infinity. What is the actual value of the distance image? Let's start with the easiest thing. Is it positive or negative? I already asked this, so it's not a new question. If the image is on the same side of the lens as the object, is it a positive or negative image distance? It's a negative. Okay, so it's got to be a negative value. And it's not going to be the far point actual because the lens is not at the eyeball. It's going to have a magnitude that's the actual far point minus that offset of 2 centimeters. So to get my sign right, I'm going to put that offset 2 centimeters minus the far point actual. So in the case of Gila, that would be 2 centimeters minus 32 centimeters equals 30 centimeters. Minus, I forgot to put the minus sign. 2 minus 32 is minus 30. So my distance image is minus 30 centimeters. My distance object is infinity. What must the focal length be? How can I calculate the focal length? I used the thin lens equation, and because I ran out of space, what's 1 over infinity, friends? 0. So that makes it easy. F is minus 30 centimeters, right? Now, do you know what your prescription is? No. Your prescription is not minus 30 centimeters. Your prescription, what are the units? Anybody know the units of your prescription? Nope. Well, here's how it goes. The power of the lens, power is equal to 1 over the focal length in units of meters, and we call that the diopter. So in her case, that's 1 over 30 centimeters. If I convert that to meters, it's 0.3. So 1 over minus 0.3 meters equals minus 3.3, continuing threes, diopters. So the prescription, based now her measurement wasn't done super fancy and accurate like, but based on her quick measurement, we can come up with a prescription of minus 3.3 diopters for the eye that she checked. Now you need to check both eyes, but that's how you come up with a prescription. What if she wanted contact lenses instead of eyeglasses? It's going to be different. Why?
There's not space between.
Because you don't have that offset. So then your distance image would be minus 0.32 meters. And so the power would be 1 over minus 0.32, which would be like minus 3 diopters, roughly. So it changes the prescription a little bit when you change between a lens versus a contact lens, eyeglasses versus contact lenses. So that's how we correct myopia. We make a lens that will create an intermediate. Is this a real or virtual image? I asked you this before, but just making sure. It will create an intermediate virtual image that you can focus on. And so that lens now adjusted so her far point with the correction is out to infinity. What's her corrected near point going to be? I'm going to add a sheet so we can actually do this. See if over break I'm going with no, they haven't fixed anything. There we go. Well, it said it was putting it the right place. We'll see. Hey. Okay, so we had the power of the lens is equal to minus 3.3 repeating diopters. So the focal length was minus 3 centimeters. And so if I put an object at her now new far point, or not far point, near point. So her near point corrected, then where's the image going to be? It'll be at the actual near point. That's right. We'll find the corrected near point by using the actual near point. And so we'll have the image So this is the near point. So for her, the near point was 9 centimeters. And what should the distance image be in that case? Two centimeters minus 9 centimeters, so minus 7 centimeters. And so then 1 over f is equal to 1 over distance object that I'm looking for plus 1 over distance image. So, 1 over minus 30 minus 1 over minus 7. I could, take 7 over 210 and 30 over 210. 30 minus 7 is 23 over 210. Nah, I must have done that wrong.
It's 9.13.
Yeah, I definitely did it wrong then. 7 times 3 is to 10. Okay. Just trusting him. So distance object is what?
9.13.
So if the distance object is 9.13 centimeters, then the far point correct or near point corrected, I have to add the 2 centimeters. Now, I relied on him to do the work, but I assume that he made no mistakes. So it moved her near point out a little, so she can't see quite as close with the corrected lenses. So she gave up a little. That's still well within the 25. I'm a little surprised, but hey, I can go back and work the numbers after class if I worry about it. So that's correction for myopia, for farsighted or nearsightedness. Now let's go to hyperopia, farsightedness. Hyperopia, again, you have two ways of talking about the lens is too weak or the eye is too short. And so what are you going to do to correct hyperopia? Okay, you need a converging lens to make it so, okay, with the hyperopia, your problem is the closest you can see is out here. And so you need to move in the near point. So it's a near point correction if you're farsighted. So notice it was a far point problem if you were nearsighted. It's a near point problem if you're farsighted. So what you're going to do to find a prescription for the hyperopic eye, for the farsighted person, is essentially the same work, except now you're going to put the object at the ideal near point. What's the ideal near point? 25 centimeters from the eyeball. So that's where the object is going to be placed. If you're using eyeglasses, that means the object distance is 2 centimeters less because the lens is 2 centimeters from the eye, so 23 centimeters for the object distance. And then the image will be at the actual near point, which might be 1 meter away. Keeping in mind that 2 centimeters would be minus 98 centimeters for the the image distance, and then you use the thin lens equation once again to find the prescription. So what we've learned here is how to find the prescription for basic eye problems, the nearsighted and farsighted. And we've also learned the unit for power of a lens. What's the name of the unit? Diopters. That's D-I-O-P-T-E-R. Diopter. And we use the capital D for diopters. And 1 diopter is an inverse meter. So it's a very simple definition. Diopter is 1 over a meter. Now, this is the way it was when I was young. When I was in graduate school, the girlfriend of a classmate had eye surgery to correct her vision. And so now I was in grad school. This was around 1989 or so, which I know to you guys is the prehistoric times. And the method they used sounds prehistoric. What they did was they cut a circle of that sclera. They have 2 ways. They can either cut a complete circle and take it off, or cut almost complete circle and flip it back so it's like got a little hinge piece. And then they took a scalpel. And this is where it sounds scary to me. The correction was, here's the cornea, and if you were the common vision problem of being nearsighted, you have a cornea that's too curved. Well, they didn't shave it down. What they did is they said, well, if we damage the cornea, you know what the body does in response? It forms scar tissue. And so they would calculate how many slices to make, and they would slice the cornea. And then they put the protective covering back on. Don't even need to sew it in place. They just put it there. It's held in place by the lack of air inside, basically higher pressure outside. And then you go home, and over the course of a couple weeks, it heals, and your vision slowly changes. Sounds barbaric, doesn't it? I was like, ain't no way in the world I'm going to let somebody just sit there and slice my cornea and hope that the scarring is just right to improve my vision. Well, these days they have a much safer way. And I don't remember, where I have the slide here. I'll come back to that. What they do today is laser ablation. I got my PhD in laser ablation, vaporizing materials with a laser. Specifically, I was vaporizing transparent materials with a laser. That's exactly what they're doing to correct your vision. So what they do now is, if you're nearsighted, they, of course, measure what the curvature is of the cornea and what the curvature needs to be to correct your vision. And then they still cut that flap, kick it back or take it off. And then they just put you under a laser that's controlled by a computer. And the computer has been fed in the shape of your cornea, and it has a little grid, and it goes zappy, 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 and vaporizes a very thin amount for each pulse of the laser. And so they just adjust where the pulses are hitting and how many pulses strike each place to resurface the cornea. So it's really a precision machining process of machining the cornea of the eyeball. And in this case, there's virtually no scarring. They put the flap back on, you go home, and you're good to go. Now, when you go home, you have to wear the little glasses that are really dark. That's because they put medication in there to keep your pupils blown during the process. And so that's just so you don't get a lot of bright light when you can't control it. So the beauty here is it's done immediately. And you don't have to worry and like, what's it going to be like in 2 weeks? I hope it gets better. It's going to be like it's going to be as soon as you're done. And of course, they have a much better control of the final shape. So this is all good, right? It is not perfect. I had a friend who was an airline pilot, and in the trade magazines, they were warning pilots, don't get laser vision correction surgery because it can have some side effects. You're basically making a grid on your eyeball because of the laser pulses. And so some people experience diffraction, that is the bending of light so that they see rainbows everywhere. And then they fail their pilot's exam because they don't have the appropriate vision. So they were warning pilots, just wear your corrective lenses. You might not be able to be a pilot if you have that surgery. So it's not perfect, but it is much better. Now, back in the day, when they were slicing the eyeball, the only thing they could correct was the myopia, nearsightedness, which was most people. But there are a few people who are hyperopic. And those people, well, then you would need to make it so it is more curved. And nowadays, they do that actually by vaporizing around the edges to make it more curved. But there are limits, because if you cut off too much around the edges, what are you going to end up with? You're going to have that cornea then broken away, and then you got all kinds of problems. One last thing, I always mention this just because it made me cry. Another thing that you can have is a corneal replacement. They actually, you get a cornea from a cadaver, shove it in your eyeball, and so people who have like cataracts can have that to correct their vision. My parents were missionaries in the Philippines, and there was a kid there who had come from just abject poverty, horrible nutrition, which had caused him to have really bad cataracts, so he could hardly see. So he worked call portering one summer, selling magazines, saving up money so he could have a corneal transplant so he could see. And so he got his money, he worked hard, had the surgery, he could see, life was good. The next Sabbath, he's at church and he's teaching Sabbath school lesson when health authorities come to the church, call him and say, you have to come with us, which is scary, right? And the outcome of this is worse. what had happened was this person had died in a car accident. Both of his corneas had been harvested, one given to him, one given to somebody else, and the other person had developed rabies. And so they were taking him to monitor, and he died from it. And it's, to me, it's such a horrible story because, he worked so hard to improve his life and it killed him. But that's another thing, and you need to be very careful with these medical procedures. Don't want to end up like him. Okay, seeing in colors. We all have we may not all have beautiful color vision. Is there anyone here who is colorblind in any way? No? Okay, color blindness, sex-linked trait, I believe. It's far, far more common in men than in women. It occurs because of our color vision. We have 3 types of cones. That's types, believe it or not. What are cones? They're light-sensing things that are shaped roughly like a cone. And they come in 3 varieties. Our textbook's picture says yellow. We always call this one red. Yellow is probably more accurate, but I'll tell you why we call it red. So if we look at these cones, this one that I called the red is the only one that's sensitive in the red region. That's why we call it red. The reason the textbook called it yellow is because its peak, its most efficient color is yellow for sensing. And notice it will sense out into green, right? Green is there where it says green, but it's the only one that is efficient in red. Then we have the green cone that has its peak efficiency here in the middle of the visible spectrum, and the blue cone that is the only one that can detect over here in the blue range. And so we see color vision because we have 3 different detectors with 3 different ranges of light that they can see. And so our brain takes that information about the range and puts it together and says, it's this color. So on your computer, you can do things like use a color picker, and you can adjust the red, the green, and the blue. Why the red, the green, the blue? Because those are the 3 primary colors of light. Those are the 3 colors that correspond to what our cones can see. And we interpret the color by how much red, green, and blue was present. So that's how we get our color vision. Now your color vision, it's also called your photopic vision. Photopic means when it's bright light is done with cones. You also have what we call the scoptic vision, which is in low light conditions. Whoops, I used quotes to. The low light vision is done with the rods. Rods are different color sensing elements that have a much broader range. Basically, the rods are sensitive throughout the visible range. The peak for the rods is somewhere in the middle. So if I were to draw the sensitivity to the rods, it'd be something like this. If it's low light, that's what gives us our vision, the rods. And you can't tell colors with the rods because there's no color or separation. So in low light conditions, you cannot see colors. I used to find this amazing. I used to have a 7-Eleven's big gulp cup that I kept on my bedside stand filled with water. So in the middle of the night, I could wake up and take a drink, right? You wake up in the middle of the night, you look over there and you can see it just fine. Why? Because my eyes have adapted to the low light conditions. I look at it and it's gray and white. Why is it gray and white and not red and white? It's low light, so my cones can't even see it. Only the rods can see it. And so I just see it as black and white. This is also in astronomy, when you look at stars, they pretty much all look the same because there's not enough light for us to see the colors. We can just see light versus dark. If they're really bright, something like, let's say, Betelgeuse, you can actually see that there's a red hue to it because it's bright enough that you can actually see some with the cones. Oh my goodness, I'm out of time. I had great plans to cover far more. I'll see you for lab tomorrow.